All right, we're just going to do a few final touch-ups on this 3D surfacing. I just want to show you a couple of items. So let's go back into that toolpath. So we had left off on technology. So on this rough, I want to show you a couple of other things. Let's go back to the simulate to re-show ourselves what's going on. Did you see that first cut? That was a monster cut. That's not good for that ball end mill, and especially for the ball end mill. So if you think about a ball end mill at the very tip of the ball, if that's spinning, if that ball end mill is spinning at 3,500 RPMs, what's that little tip at the middle spinning at? 0, right? So that little point at the end, no matter how fast you spin that tool up, is theoretically not moving. So ball end mills don't like to plunge down into material because the middle isn't moving. So if you're not moving, you're not cutting, you're just pushing. Okay? So you want to kind of minimize this plunge aspect here. So one thing that'll help you there is look at this Z entry. So you can define your strategy for how you're going to move into this part in the Z axis. We had none. You could do kind of an angled thing. You could do a helical thing where it spins in, or kind of a linear thing. Let's pick angle, and then you can set the angle. Let's leave that to 5, and then let's calculate that and see what that does. You see that? That was a much more friendly entry. Okay, it's still got a little aggressive down here, and the reason for that is this step. Okay, so if we minimize that, let's make that 0.05 and recalculate and do that as well. You see how much friendlier that looks to the tool? And it's kind of just hogging that all out, and it's leaving 20 thousandths up by this surface here so that we can finish that off later. Okay, but this is a much friendlier path for this tool. Okay. Mode, this was in pocket, so if you go back and look at that, it's kind of running around this path in kind of this pocket style. You could do it in a profile style. We'll hit approach from the outside, and you can see that difference. It's not going to be all that different up at the top. It'll be different, a little bit different down at the bottom. Okay, and here you can see those scallops I was talking about. You see those? Because we're roughing, you're going to be left with these scallops, and you're going to have, it's going to feel rough, and that's where those surface finish gauges come into play. So typically you're going to want it smoother than that. Maybe not. Sometimes when you're gluing things together, you want some ridges in there to increase the surface area for the glue to adhere. But most of the time you're going to want it smoother. All right. Data, you can decide if you're going to zigzag across or if you're just going to go one way. Other types of angles. In this case, the hatch angle was 90 degrees. So if you look at that, it's cutting in one direction. We can change that. Let's say to 180. See what that does. See how that changes that path up a little bit. Okay. All right, so there's the roughing. Now let's just say we didn't rough. Let's not rough. And remember, I said that's okay sometimes, because if you do it right, you're taking just a few thousandths of material at a time, so you don't have to rough if you don't want to. So we're going to do a no roughing pass. But in this case, all right, so we're just going to do a finish pass. Let's do linear, let's say. You see what that kind of does? You can pick other ones like spiral, depending on the type of surface that you have. Here's that constant Z again. I'm going to do linear. You can see it kind of runs these lines up and down this way. If you only do a finish, you need to be very careful about the parameters you set, because if you plunge in too hard, you can break the tool off or screw up the part. So you don't always have to rough, but if you don't rough, you have to be very careful about how you do it. So you definitely want a Z entry strategy. And then, so this angle along path, I believe that is just the angle at which it's going to go across here. So look at that, look at that right there. That would have probably broken the tool, just plunging in and taking all that material at once. So we can't have that. So either you would have had to done a rough, or we've got to redefine these parameters carefully. So let's check data. So data is going to help you force this tool to work the way you want it to work. So first of all, the step over, that's really critical. That's that one that's going to determine your smoothness, your heights of your scallops. Okay, so we want that to be small. 5 is probably okay. Again, this is the distance step over. If you wanted to just define the scallop, you can do that too. I like doing the step over. I'll keep it at 5. That's okay. I'm okay with zigzagging as long as I take that small amount of material. All right, direction angle, or direction defined by an angle. We're at 0. Let's watch what that does. Again, I think it's going to take this big nosedive here. Yep. So let's try 90. And again, that's okay too, but it's really taking a big plunge there at first. But now, if you look at it now, all the rest of these passes are okay, because all I'm stepping over by is 5 thousandths at a time. I'm just going 5, and then it goes up, 5, down, 5, up, 5, down. So I'm only taking 5 thousandths here. For the rest of this path, that's okay. That's not going to hurt anything. But really, I'd rather go left to right. Start at the top and work our way down to the bottom, and then it wouldn't take so much material. Where is that? I may have to find that for you. Oh, there it is. So here I had this 360. Let's try that. Oh, why would it close out my file? Well, I guess we're closing out the file. All right, so let's go back. And we'll simulate this. And see, it's going to move across and take small little passes back and forth. If you do it that way, you can machine the whole, you can take all of it at once, because you're really not taking all of it at once, you're just taking little bits at a time. But you got to make sure that you write the pass so that it starts up there. If you don't want to do that, you can write a roughing pass. Okay, there's that. Let's see. I want to show you how big these files are. So let's generate G-code. Here it is. So look at this file. It's 12,000 lines. Okay, because every one of those little steps is a move, is a linear move. So these files get very large. Let's save this to the desktop and just look at the size. This one probably isn't all that big because this clip is this big. But what if this thing was a wing section that you had that's this big, 10 inches cord, you know, 2.5 foot span? These files can get monstrous, which is a problem. So this thing's not that big a deal. It's 152K. But imagine this being 2 feet. Okay, so these things can get big. Yeah.
How long does a little part like that take to machine?
Let's check it out. Let me finish this thought and then we'll do that. So a couple of our machines have file transfer on floppy disks. 1.44 megabytes is your limit. Okay. Veil has a USB port. So if you have these monstrous big 3D surfacing paths, you're probably going to have to run on Veil so that you can put a 4 gigabyte drive in there or whatever. Okay, so think about that if you get to that point. How long do they take? Good question. We can look at that in simulate and show data. Remember that? And I'll just speed it up and blast it. Hour and 9 minutes. So these paths are not very efficient. Now we could probably get this one down. You can do some stuff like checking your speeds. My feed was 4. It was the default. So we can go 50 and 50 the way it's set up, right? So let's try that again. That's going to help a lot. A lot. Three minutes. Okay. So speed is a factor, but you're kind of limited on speed to the 50. So over large pieces, that's not going to help you as much. The other big parameter that's going to do it is your step over. So if I step over by 2/1000ths of an inch, I'm going to have that many more lines of code that I have to run. If I step over by 20 or 200,000ths of an inch, you see I'm going orders of magnitude down, up in step over size, down in time. What you sacrifice for that is surface finish. So you have to determine what surface finish am I okay with and what am I not okay with. So for aluminum, this was a small step over. I think they stepped over for this. I think it was a 0.5 or 1,000th. Okay. For foam, you might be able to get away, especially if it was like a wing section. You could get away by stepping over by a lot, 50, 100,000ths. And then when it comes out of the machine, you can just lightly sand off all those scallops. And sanding foam goes really quick. Sanding aluminum doesn't go so quick. Okay, so with 3D surfacing, it's a big trade-off between your step over, your surface finish, and your time that you have. So you have to decide. Okay. Only last thing I wanted to show you was, and I don't know if it's going to let me do this. Let me go back to my solid model and rebuild it. It was acting finicky on me before. Yeah, it's doing it again. So that other part I had, let's see if I can bring up that other part. I wanted to talk about the hole. Let's see if it auto-save this at all. Yeah. See what happened at the hole? It kind of went over the hole, but it didn't really. It kind of skipped the hole. So it left some material. Okay, there's a lot of ways to deal with this. So one way to deal with this is, and this is probably the way I think I would have done it, is I would have squared up this block like this, and I probably would have drilled the hole first. And then you don't have to worry about it. That's one way to deal with it. Now, one thing that complicates that is the angle. So if you were to drill this hole right here, you're kind of going to be coming down right on this corner, and drill bits don't like that. They deflect. So you would have had to kind of machine a flat there and then drill the hole. And then what else becomes an issue with that hole, drilling that hole right now? What's that?
Fastening it down.
Fastening it down, yeah. You could hold it in a vise between this face and this face, and that would work. A couple of other problems is setting that angle, which we can do with a sine bar. And another problem is positioning the center of that hole. So we'll have to, the only way we're going to be able to do it is to edge find on this edge and do the trig to get over here at that angle to get that center of that hole, which we can do, but you're going to have error based on how you filed this edge, because this edge in SolidWorks is infinitesimally sharp, but I bet it's not sharp on your piece. I bet you filed off a bunch of material there, which could be several thousandths to 15,000ths depending on how you did it. If you hack that out on the belt sander, it's gone, right? So there's advantages and disadvantages to that method. The other method is you can go into SolidWorks and you could suppress that hole, rebuild it, and SolidCam should ignore the hole. I say should carefully. I've had some issues with this guy. Yeah, that's what I mean. It still didn't do it. It still thinks it's there for some reason. And I can't remember what I did to deal with that. I think we had to, oh, you had to synchronize. So you can check synchronization with the SolidWorks model, and it says, hey, you have a rebuild problem here. You changed something over here, which is suppressing this hole, and I'm not cool with that. I need to be rebuilt. So you go to synchronize and hit synchronize, and then it still has this asterisk. It's not calculated. You could have done synchronize and calculate, but we'll go ahead and calculate, and the little asterisk goes away. That should solve the problem. There it is. Okay, so you would think that if you suppress something in SolidWorks, it would automatically update, but sometimes you have to use this synchronize feature if you suspect that SolidWorks and SolidCam are not communicating properly. Sometimes you have to use the synchronize feature. I think they auto synchronize. If you were to save this and reopen it, I think it auto synchronizes as part of the startup feature in that file, but I'm not sure. Any questions there? Okay, that's about it. What you're going to do, who's a junior going to be a senior and remembers this? Remember this thing? Mm-hmm. So Trudy and Bobby spent the last semester. Remember how you had to determine altitude? How did you determine altitude?
With triangle things.
How accurate do you think that was?
Not.
Well, Trudy and Bobby spent the last semester coming up, developing, I think on pat with me, a onboard altimeter that uses a pressure transducer and logs data onboard to flash memory as the thing's flying. And we've tested it, and it works freaking great. It is sweet. So you get this really nice profile back, and you can we think we've gotten the accuracy to within a few feet. And there's no way you got that accuracy to a few feet with that little angle thing you had. Yes.
So is there a bolt hook in the bottle? Is that what I'm saying?
No. So it's a little, the altimeter itself is a little pressure transducer, and it's soldered onto a PCB, and also it's got a little battery pack on it to power it, and it's got flash memory on it, so all that's there. So we had to find a way to put it on the bottle, and it couldn't mess with the aerodynamics because that's part of the lab, right? And it couldn't mess with the mass because that's part of the lab. So what we came up with is a mount. So we're going to mount the, and it also couldn't die. It had to survive the impact, which on some of them was pretty brutal. So we came up with this. We started with this high density foam that's machinable, okay? And we put a little pocket on the back, which is where the PCB is going to fit. It's a 1.5 by 1.5 inch PCB. You can feel the foam, kind of squeeze it. It's a very high density foam. And we use SolidWorks to make a model of the bottle. And then we mirrored the bottle using the mold making tools in SolidWorks. And you're going to machine this little mount, which we then glue to the top of the bottle. And then the altimeter sits in the top. And then we have a cap, which you're going to build on the lathe. Okay? So you're going to build this piece, and then we'll glue it here, and then you'll put a cap on top, and that protects the altimeter. And it also allows the students to do their own little nose cone design. I don't know if you guys were allowed to do your nose cone designs. This year we weren't, because they would make these kind of wimpy ones, maybe with party hats or something, and with the altimeter in there, it would crush the altimeter. But with this new high density foam cap, it won't crush the altimeter. Okay? So we're significantly upgrading this lab, and you guys are going to help us build it by learning how to do 3D surfacing. So I can pass that around. Any questions there? So that piece that glues to the this bottle and the cat are going to be homework 18. So, and I believe that's due the last day of class. So it's a 3D surfacing op and a lathe op. We're going to set up Wolf Creek to do the 3D milling op. Questions? And if you don't have any more, we're going to go in and I'm going to show you the particulars of that. And then that's it. In the third segment, we're going to swap and you're going to do the lathe tutorial with Professor Hodgkinson. All right, let's head